Um, okay, so I want to talk about function transformations and how these visually affect the graph of the function. For example, translating vertically, horizontally, stretching vertically, horizontally, doing reflections about the x or y axis. Like these are the things I want to talk about. So, like if we have function f of x, then I will first I'll talk about translations, then I will talk about and like translations will be like probably the majority of this video, and then whatever kind of treatment I give it, I will kind of do the same if I have time or feel like it for the stretches, like stretches. And then, like reflections, I doubt I'll really do this much. But but basically, if you're able to get translations, I feel like that's kind of the hardest. So examples of translations, they're basically kind of like four main examples, or I mean two. Like we have vertical, which is like actually let me just undo that. So like g of x equals f of x plus 1. I mean, I could also do like minus 1, but that's one example. Another one could be like another example could be like f of x minus 1 and or f of x plus 1, and these are both horizontal, where this one, so like that's an example. So this one is vertical translation. So I will talk about or at least explain how I reason about it. Why does this, why is GFX? Like if you look at the graph of FFX and you look at the graph of GFX, why is the graph of GFX like vertical translation down by 1 unit? And then for these guys, like if you look at compare the graph of x to the graph of f of x minus 1 or f of x plus 1, why are these circled graphs like the same as graph of f of x, but shifted like one in either direction? So I want to like kind of explain why that's true. And I want to do the same for for stretches. And then reflections, I might briefly talk about at the end using whatever same techniques I develop for translations and stretches. So like stretches, an example of that could be like if you're kind of vertically stretching, we could kind of squash f of x vertically down by a factor of 3. So that's like vertical, vertical. And then similarly, we have f of 3x, right? And this is horizontal. So what this like when I say vertical, this is kind of like squashing it down vertically by a factor of 3. And this one here is kind of squishing it horizontally by a factor of 3. This whole reciprocal thing is I will get to that, and I will also get to the like details when you look at the translations. Like I will kind of explain like why like this sign here might like these circled signs might be a bit confusing, and I also want to kind of unify or explain that it's like the underlying like there is some reason for this and how it's all the same thing in reality. So to do all this, I want to first talk about like well, let me start with vertical trans let me first start with translations, And the first thing to really talk about is compositions. Com- Compositions, composite, like a composite function. So like this right here is kind of this is how I will reason with translations. Like I want to kind of view it as a composite function. In fact, all of these three things are going to be composite functions. So typically for translations, there's two types, vertical and horizontal. So people find vertical to be like the most intuitive. So I'll kind of start off with that. So vertical translations. Well, actually, no. What am I doing? I'm first talking about a composite function. So composite function, uh, there are basically two parts. There's an outer function, function. Let me just call this, let me be unimaginative and call this outer effects. And there's an inner function, inner function, inner effects. So these outer function, inner function are just two functions. Like they take in some input, which is the thing inside this bracket, and they spit out some output. So those are just two ordinary functions. So the composite function is basically like I'm calling it outer and inner intentionally because the composite function looks like this, inner effects. And don't worry, there's a reason why I'm doing all this because at the end of the day, all these different things, these transformations, these three types are all, I'm going to express them in terms as a composite function. Okay, so outer of inner effects, right? So essentially there are two steps, right? And I'm going to like kind of draw them in arrow signs. So let me first take a step back and say like, what does f of x mean, right? Like where f could be like the inner, like the outer or the inner. So f of x simply means that we take some input, which we can call x, whatever isn't like this could be like the input name is just x, like that's kind of the canonical input name, but it could literally be like f of triangle. Like it doesn't really matter. Like this could be like equals triangle plus one, right? Or f of x equals x plus one. Like it's just whatever's inside the parentheses is the input. Like because like notice here the parentheses is not x, but it's inner of x. So that's kind of why that's anyway. So anyways, x, right? So f of x basically means that we have some input, which I'm going to call x or input, and we're kind of hitting it with this function f, and it will return f of x. So that's kind of like a one-step function. So what are the two steps now for composite functions? So what about outer of inner effects? So here, let's kind of so here the input of this, like this whole thing is a function of x. So we have some input. So now there's two steps. First, we hit this input with the function inner, and this will give us some output, which is inner effects. And now this output, the output of inner effects is the input of outer. So this kind of intermediate variable, it's a bit of a tongue twister, but this intermediate variable, which is like it's the output of the inner function, but it is the input of the outer function. Basically, there are two steps, and then we end up getting outer of inner of x. So that's how you evaluate a composite function. In the so composite function, there's two things, an outer function and an inner function. And then we basically do two steps. Like step one, uh we um we hit input with inner, and this gives us some intermediate result to get inner effects. Then to like hit result, like the intermediate result, which is inner effects. Again, this inner effects is that guy, right? So like, and then we hit inner effects with outer to get answer, to get the result. So these are the two steps. So um let me just actually do an example, and this will be related to horizontal or translations, but this is, I mean, yeah, let me just start off with an example. So let me have outer be defined as the doubling function. So let me just have outer defined as outer of x. We'll basically take x and take its input and basically double it. And let me let the inner of x, like let me let this function be like we take our input and we basically increment it by one, right? So now what is outer of inner x? Like what is this thing, right? So that's kind of what I want to do, what I want to ask. So here we have some input and we hit it with inner, which would give us x plus 1. And then we hit it with outer. So now this x plus 1 becomes the input. It becomes the input to this. So this thing becomes the input to outer. And that, and outer simply takes its input and doubles it, right? Outer just takes the input and doubles it. So what this does is, well, our input is simply x plus 1, and then what we're doing is we're doubling it. Like this thing here basically is kind of mirroring that guy, and we're done. I mean, we could also, so like, so basically, like, let me just let g of x equal to outer of inner of x, so I don't have to keep writing that, right? Then g of x basically equals 2 times x plus 1. So what does this g of x mean, right? It means we take our input, which is x, then we hit it with x plus 1, so we add 1 to it, we increment it by 1, then that result, we double it, right? We do the parentheses first. Now, of course, we can expand this and like distribute it out as 2x plus 2, or we could kind of factor it and bring it back in. Anyways, so like there's like, but this is kind of what it means to be a composite, a composition function, right? Also, like sometimes I think it's another notation, outer, like this weird open circle, not to be confused with multiplication of inner, which is the kind of like the same thing. But anyways, and also we can kind of view this like you see how like we have like this results here and that result there, like they're both GFX. Like we can kind of view this as just a simple binomial, like just a polynomial, or we can view this as a composition, and we can kind of show this visually. Like let me kind of have the outer function, because at the end of the day, like outer function is called. So here, let me just kind of show GFX visually. So let me start off with just like the outer function. We have x, and we're basically doubling it. So we can kind of view that as the area, right? So this is like 2x, right? But let me, so then now we could instead first add 1 to x to get like this new side length and then double it, right? So that kind of like we first compute this side length and then we hit it with a double to get like the total area, which is like this area plus this area. And kind of so the area of the bigger rectangle here, again, where this is 2, like pretend this is all like a rectangle, not a parallelogram. But anyways, so then, so this view of it is like this way of showing g of x. Like first we take our x, then we add 1, and then we kind of double it. But another way of showing it is this variation here, where we first take 2 of x, and then we just add 2, because the area of this guy is 2. So, like, I just want to say that, like, for g of x, like g of x could equal, like, basically this whole, like, 2 of x plus 1. Like, we can kind of view g of x as like a composition of outer being doubling, doubling, and then like inner being like a doubling function, and inner being increment function. So we can like view it like that, or we can just kind of distribute the two and view it as a just a normal polynomial function, just a simple linear function in slope intercept. Anyways, so that's what composition is. So now that I've kind of tackled that, let's talk about translations. So let me start off with vertical translations. Translations. Okay, so um, we have ugh, we have let me call it g of x equal to f of x plus 1. So this is a vertical translation of the graph. Like if you look at the graph of g of x and the graph of f of x, uh, let me just kind of draw some graph here, like that. That is going to be f of x. Like that's going to be f of x. And then if we kind of take any point here and shift it like 1 unit up, so like let me call this k, and let me call that guy f of k. Then if we kind of add 1 to it, so then this point here would be f of this vertical thing would be f of k plus 1. So like this point, like for each point here, we kind of like we would like essentially so this graph here is f, the bottom one is f, and then the top one is g of x. So this is kind of how you kind of go from this graph to this graph by just by moving everything 1 unit vertically. So I mean, why is that? So essentially the strategy I will do to talk about all these transformations is I will consider just like kind of like just one point on the graph of f. So this point belongs on f, and there's in this point here will mandate another points here being on g. And like because this kind of holds for all the points on f, I think like so because like this one will hold here, and like for this point here would kind of so this point here mandates this point here mandates the existence of that point. So like on some continuous interval, like let's say kind of like here to here, like these guys here would kind of mandate like these guys there. Anyways, the point is like okay, let me actually the idea is that a single point, as I'm showing here, I just want to consider like one point here, k comma f of k. Like this is k comma f of k. And then I want to show how like this point mandates the existence of a different point on g of x. And if you kind of look at the active transformation, like how do you get from this point on f to this point on g? So like this is a vertical translation by 1 unit up, like 1 unit vertically, like going more positive on the y on the output axis. So that's the basic strategy. I'll consider some general for any points on this. I'll kind of show where it ends up, or I will show where this point like this point forces the existence of the point on top. So why is that? So back to compositions. Let me just not waste time. So g of x equals f of x plus 1. So here, like again, it's a composition. So the inner function is simply inner of x is just like is f of x. Like inner is f, like inner equals f. So inner of x could be described as take f. I mean, take our input x, hit it with f. Hit it, I'm just using as a shorthand for plugging it into. Hit it with f to get f of x. And then output is, well, it's the familiar function we saw earlier, right? Outer is this incrementing function. So that's kind of what outer is. So outer is you just kind of outer effects, like you take your input and you simply increment it to x plus 1. So that's outer effects, right? So then if we come, so for g of x, we can view it as, well, we first take our x and then we call, like again, two steps. Like inner and outer is like kind of order. Like we first do inner, then we do outer, right? Those are like the two steps I talked about earlier. So here we hit it with f, which is the inner function, and this gives you f of x. And then the outer function here is we increment by 1 to f of x, which is the input, plus 1. So now let me like so example, let's just say that like so let's just say like what is g of 5, right? Like what is g of 5? Well, here we start off with 5, we get f of 5, and then we get f of 5 plus 1. Again, I'm merely just merely using that pattern, right? So let me consider some value k, or yeah, let me consider instead of 5, let me consider uh like g of k, like some k. So for some input k, you would first get f of k, and then you would get f of k plus 1. That is the points k, which is our input, and our output here. Or sorry. I'm so sorry about the way. No, that's wrong. That's wrong. No, I was making plus 1, right? So that means that for g of k, the points, like the graph would have k, which is their input, and then it would have as their output f of k plus 1. So this point here is point on g's graph. G's graph. And notice that the point kf of k f of k is a point on f's graph. So here, let me just kind of draw out k and f of k, and like this, each tick is one separation. Then here, this is again kf of k, which is on f, and this here is on g, right? So thus, this function here, g of f of x plus 1, basically for all the points on f, there's going to correspond to like g will be 1 above it. And this holds true for any k, basically, for all k, right? So this explains how like for any other point on f, you would have another point on top. So, and again, and now we can do the same thing for like, sorry, g of x equals to f of x minus 1, right? So now we basically take our x we hit it with f of x, which would be like this ordinary point, which is on f of x, but then we subtract 1. So this point is on f, and this point is on g. So like just by this example itself, we can see the effect of this kind of this g of x being kind of shifting down by 1. So like what was the whole point? You might ask me if like why did I kind of model this g of x? Like why did I model it in terms of this kind of composition, right? Well, so again, this one, so like the reason why, I guess, is because, well, let's talk about horizontal translations, which are harder. Horizontal translations, right? So like, let me kind of take a step back. So here, this thing here is shift down by 1, and then gf, and then if you have f of x plus 1, then this thing here is shift up by 1. So like this thing here kind of is up, and this minus sign here is for down. And again, this 1 is by how many units you shift. Now, horizontal translations are a bit more, I guess, confusing at first to most people. So if you have g of x equal f of x minus 1, then this minus you would expect to equal left, right? Because like here the minus, because here like this minus sign here was kind of down, like in the negative vertical direction. But here this minus sign actually means shift right. And that's a bit counterintuitive. Like why? So that's where com this whole kind of composition idea here, like that's where this thing is going to shine. So notice here, it's like you first hit it with f, then you increment it. Well, now let me have g of x. Again, let me kind of rewrite that as f of x minus 1. So now the kind of outer and inner swap roles in a sense. So now the inner function, so g of x I'm basically modeling as a composition, where the inner function is first we increment, or sorry, decrement. So inner of x is basically we take x and then we decrement it, decrement to x minus 1. And now our outer function, so it's like inner and outer kind of swap roles, is f of x. So our outer function is simply we take x and then we just get f of x. So now we're using this kind of inner outer, like this composition. Here we have our input, and then rather than immediately do f of x like we did for the vertical translations, we kind of first we do the decrement or increment, whatever. We do a decrement to get x minus 1, and then this result here that we get, we plug that into f of x, we hit it with f to get f of x minus 1. So this here kind of resembles this guy here, but with these two roles a little swapped. So again, like they're both kind of a two-step composition where there's like an inner and an outer. Like we first do the decrement, the inner, then we take the output of the decrement and make that the input of the outer, which is f. So what is the whole point of this, right? Well, let's kind of do the same thing. Let's kind of do like, how do we get g of 5, right? So to get g of 5, we first take 5, then we decrement it to get 4, decrement it to get 4, then we plug that into f, and that gives us f of 4. Now we could do this for 3 too. Let's just start off with 3, then we decrement it to get 2, which is the step 1, the inner function we decrement. Then we plug it into f to get f of 2, right? So that means like so like the point so that means like this thing implies that the point 5 comma f of 4 is 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 on G, G's graph. And then like 3 comma f of 2 is also on G's graph. So in general, like obviously like 4 comma f of 4 is on f's graph, right? Like when the input to f is 4, then the output to f is f of 4. So this is on f. So like let's kind of generalize it. So let me just put a k here. So if we have k as the input, not to G, but I want k to be the input to f, right? So then when we have some input k and we hit it with f, we're just going to get f of k, right? So now the question is, what is the input to G such that the input to f is this k here? And we can kind of like just it's kind of obvious, like I mean, well, I shouldn't say obvious, but if you look at like when the input to f is 4, then the input to G is 5. When the input to f is 2, the input to G is 3. So in general, there's a relation between 3 and 2, 4 and 5, and that relation is pretty much kind of specified by this inner function. The inner function relates the input to G, which is x, to the input to f. So x minus 1 is the input to f, and then x is the input to G. So basically, just from this definition, right, like here, x to x minus 1, we can see that the input to G is always 1 more than the input to f. Like, if I were to call this question mark, then like question mark minus 1 equals k. So obviously, question mark is k plus 1, right? That's we can just kind of equals k plus 1, can add 1 to both sides, right? But essentially, like this question mark here is k plus 1. So it's like we're looking at this inner function and like given some output here, what is the input like given like the image here, what is the pre-image? Like given this x plus 1, what is the input that generated the x minus 1? So like it's kind of like the inverse function. Like given that the input to f is k, the input to G must be, it's mandated that the input to G is 1 greater or k plus 1. Because that way, like adding 1 undoes the subtracting 1, which it undoes this decrement right here. Again, this is very obvious, right? If A is or if you kind of if let's say if A is less than B by 1, then B is greater than A by 1. Like that's a very obvious statement. And that's essentially what's going on here. So to get g of k, right? To get g of k, we basically, or sorry, to get g of some k plus 1, we do this step right here. We first take our input, then we subtract 1, we plug it into f. So the reason I started off with k here instead of like k plus 1, like I wanted k to be the input of f. And the reason why is, again, the same approach. I want to consider the points k, f of k, which is on the graph of f. So this one here is on f. But here, g of k plus 1 is f of k. That means the input to g, like this pair, right? So the input to g is k plus 1, and the output is f of k, right? I've established this very, very tediously made this clear, hopefully. So like we have this coordinate pair x plus 1 f of k, and this coordinate pair must be on the graph of G. k plus 1 is the input, right? That's the input. And the output is the exact same. So this point here is on G. So we're done in a sense, right? So like for any k comma f of k on F, there must be the point k plus 1 comma f of k on G. Because it's like for the input of f to be k, the input to G must be 1 greater than, so that when you hit it with the inner subtraction, we get the k. So that is kind of how it works. So if you have some function here, let's say like this function here, then this on f, so that's f, then this point here, right? For this point here, if that were to be k, then we know that this point here must be on G. But we could say the same for any points, right? So like this point here gets shifted, this point here gets shifted, this point here becomes the vertex, that point here, and so forth. That one gets shifted, and so this ends up kind of having a translation. We shift it to the right by 1. So I've kind of shown now that this thing here means we shift graph of, or not shift, let me call that translate. Translate, shift, whatever. Translate, I just want to use translate because it's translation. Graph of f, 1 unit to right. Similarly, g of x equals f of x plus 1, right? So this would be shift left. Because here, right, if like, because here, like the input to g of x, so like here the inner is increment. So first we kind of take our input, we increment it to x plus 1, then we hit it with f to get f of x plus 1. For example, if x is 5, then the input to f is 6, and so it's f of 6, right? And then in general, if the input to f is some k, right, that means f of k is the output both to f, but the input to g such that the input to f is k minus 1, right? Like if you look at 5 and 6, 6 is greater than 5 by 1, so like k minus 1. This off by 1 in this direction, uh, we can just look at the sample point 5, like the sample point here to figure out that. I mean, yeah. So again, like for some input k, f of k, which is on the some point for any point on the graph of f, right? There must be the point k minus 1 f of k on G. So this is on f and that's on G. And again, if you kind of, since this applies to any point on f, that's why like we look at the action of this point here, like this point here mandates that point. If we do that, like that's why the graph, that's why this is a left shift, right? So I'm basically done with that. Now, you might kind of wonder, I was like, okay, so like, how come like here the negative sign, like how come here plussing here is left, but then when you kind of recall the vertical ones, plussing goes like up, like kind of adding on to the y direction, right? Well, I actually want to say that they're actually the same thing in a sense. Like, um, huh, I want to like, okay, so far I've been kind of like, if you have like, I'm gonna talk about like an implicit representation, like rather than y equals like, I don't know, like x or yeah, I'll do 10 minus x, right? So like here it's like x is the input, y is the output. I'm gonna do something called implicit. So I'm gonna like here we could have like, again, we could have f of x be equal to like 10 minus x, or y equals 10 minus x. I'm going to kind of, I'm going to instead do x plus y equals 10. So I'm going to call this like, I'm going to have this be the function f. So this will be the function f. It's going to be a linear function, right? We could all obviously say that y equals 10 minus x, right? And then this would just be a simple graph, right? Right? 10 minus x, or like slope -1, y-intercept 10. But so here I could instead like define g, where I want g to be shifted right. So like by 1. So instead I could have like x minus 1 plus y equals 10, right? Where like this whole minus business is like the same g of x here. It's like we're replacing x with x minus 1. So here, actually, let me go back to f, right? So let me just name two examples. Like when I say that f of x plus y is 10, basically, like it's kind of a constraint, right? Like any such x and y that satisfy this constraint is on the point. So it's a different way of describing the graph of f. Like here, I think you call this the slope-intercept form, and this one I think might be called the standard form. Like that's just like a different way of saying the same thing. So like two numbers. Let me consider 6 comma 4, right? If that's x and that's y, right? 6 plus 4 equals 10. So because of that, 6 comma 4 is on f. So 6 comma 4 is on the graph of f's graph, right? Now um for g, uh does 6 comma 4 work on g's graph? On g's graph? Well, no, instead, right? So like the y value, we're gonna plug in 4, but what is like this entire term, right? Needs to be equal to 6, right? Like as we saw here, when this term is 4, this term is 6, right? In two terms, their sum adds up to 10. But here, this term is 4, then this entire term, like this whole x minus 1 business, this entire term must equal to 6 for the same 6-4 relation to hold. Because like here, like 6-4 works. So here, like the result of x minus 1 needs to be 6, which implies that x must equal 7, right? So 7 comma 4 is on g's graph, right? Because we can test it, right? 7 minus 1 plus 4 equals 10, right? 6 plus 4 equals 10. Yep, that's correct. So let's plot this, right? 6, 1, 2, 3, 4. So 6 comma 4 is on F, and then 7 comma 4 is on G. So that's why G is F shifted to the right, right? Now let's kind of go back to F, right? So F would be x plus y equals 10. So like so here like replacing x with x minus 1, this versus this resulted in shifting right by 1. So now here, let's kind of shift y kind of not to the right, but up by 1, right? Equals 10, right? So here, like so now here, like we know that 6 comma 4 is a point. So here, this would still be 6, but this entire thing would be 4, which means implies that this, so like for g, so g equals f g of x equals f of um or um sorry here uh so here g so here this g of x equals f of x minus 1, because this x here that we took here, um what am I saying here? So this x here becomes that one, right? So now what I want to do is to have a different g, where instead of like replacing the x, like the x will stay the same, but now the y would become y minus 1. Like x plus y is 10. Like, in fact, like it's its own inverse. Like we can swap the roles of x and y. Like x and y is same as y and x, like y plus x. So like that's why we're kind of doing a symmetric thing. Like we're just uh we're just replacing y with y minus 1. So we know that 6, 4 is on the graph of f because 6 plus 4 is 10. But then for y, again, x would be 6, but then y minus 1 needs to be 4, which implies that y equals 3. So the point 6 comma 3 is on graph of g. So this minus sign is actually we're going upwards. 1, 2, 3, 4, 5. No, no, yeah, we're going. Wait, no, sorry. Wait, what are we doing? Okay, let me just plot it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So this point is just 6, 4. This point is on F, and then 1, 2, 3. So this point. No, 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 no. I'm so, no, no, no. That's wrong. That's wrong. That's not the implication. So what am I doing? So if this entire thing is 4, right? That means that y equals 5, one more, so that when you hit it with the minus 1, it becomes 4. That is 6 comma 5 is on G, right? Again, we can test it, right? 6 plus 5 minus 1 is equal to 10. 6 plus 4 is equal to 10. Yep, that is true, right? So here, this minus sign applied to like that would result in shifting up by 1, because 1, 2, 3, 4, 5, 6, 4, 1, 2, 3, 4. So 6, 4 is on F, and then here 6, 5 is on G, right? On G. So that's kind of, so like here, if you kind of do y minus 1, you replace y with y minus 1 in this kind of explicit like constraint formulation of G, then this minus sign means you're shifting up. Just like here, in the implicit form, like here, this minus sign, like replacing instead of x to x minus 1. So here, this minus sign means you shift it to the right in the direction of the x-axis, positive, like going right, going right. And then here, this y minus 1 means you're going up. So like in that sense, like now the signs are consistent with each other, right? Like if you go to the right one or you go up one, like that kind of makes sense. So like here, like y equals f of x, right? We're going to replace y with y minus 1 equals f of x, right? So doing this means we're going to the right by 1. No, no, sorry. Doing this means we're going up by 1, right? And then we just add 1 to both sides. Y equals f of x plus 1, right? Just do plus 1 plus 1. So that's kind of, so that kind of shows you how the signs are actually consistent, because y equals f of x plus 1 is the same as y minus 1 equals f of x. So it's like the signs agree after all, because here the minus sign means go up 1, but then if you look at like y equals f of x minus 1, where we replaced x with x minus 1, then here the minus sign means go right 1. So in that sense, these signs do the same thing. Now, okay, it's 11:01. It's almost an hour. Um, I'm just going to pause it here and work on the vertical, like, I mean, the stretches later, but the bulk of the work is being done on translations, and these same principles I'm gonna treat them the same way. So yeah, that's all for now.